In this video, we're going to walk through one of the rotational inertia problems that has a rod and then is connected to a hoop. So consider a thin uniform rod of mass m and length L. Show that the rotational inertia of the rod about the axis through its center and is perpendicular to its length is 1/12 ml squared. So remember that if we want to find the rotational inertia, we're looking for I, and that's the sum of the mr squareds or the integral of r squared dm. And what the uniform tells us is that because m and r are related, as you remove the radius it changes the mass, or vice versa, we need a connection to deal with density, where our density, that's linear density, is the change in mass over the change in the radius. So now we can plug in the dm being lambda dr and say the integral of r squared lambda dr, which should be the same as saying the integral of r squared dr with lambda in front. Once we integrate that, 1/3 r cubed and lambda in front again. Now this is a definite integral. We're rotating around the center point. So to go into the left, we're going to have negative L over 2. Going to the right, we're going to have positive L over 2. Negative L over 2, positive L over 2, which means that we're going to have lambda 1/3 of L cubed over 8 minus a negative L cubed over 8, which ends up being 2L cubed over 8, or 1/4. So 1/3 times 1/4, we end up with lambda 1/12 L squared, L cubed. And then our lambda, since it's a uniform rod, we can say that it's also equal to the total mass over the total length of the rod. So if I substitute that in, I'm going to get m over L, 1/12 L cubed. My L's, one of them will cancel out, and I'm left with 1/12 mL squared. The rod is now glued to a thin hoop, which means we're going to change this moment of inertia by adding a hoop's moment of inertia. It has a mass of m and a radius of r over 2. The centers of the rod and the hoop coincide at the same point. The assembly is mounted on an axle P and perpendicular to the page. So what's the new rotational inertia of the total system? Which means that my new inertia is going to be the rod's rotational inertia plus the hoop's rotational inertia. So I'm going to end up with 1/12 ml squared. And then remember that a hoop is the same as a disk, which is the same as a point mass, because all of the mass is stretched out on the edge. Then it's just going to be mr squared is the general equation. Well, we have our m value, it's m. We have our r value, which is going to be L over 2 squared, which ends up being ml squared 1/4. So 1/4, 1/12, this would become 3/12. Add that to 1/12, and I'm going to get 4/12 ml squared, which is the same as 1/3 ml squared, and that's my new moment of inertia for that combination. So now at the bottom here, I have several strings of wire that are, or of string that are wrapped tightly around the circumference of that hoop. So I have my hoop, and I'm going to wrap a bunch of strings around it, hang a string down. The system is at rest when a cat grabs onto it. So here is our cat, and sorry, I'm terrible at drawing animals, but there's my cat hanging off of the bottom. And when I look at that, the first thing I think of is I'm going to have to deal with forces. The cat is putting a force on the string, very much like an Atwood machine that we did in the past. Then there's going to be a force on this hoop that is causing it to rotate. And as I look into that, determine the tension of the string, it looks like that's the right direction we want to go. So I have a cat that's going to have a tension on the string, going to have a weight of the cat, and then up here we're going to have the tension on the string that's causing that to rotate. So since it's in linear for the cat, I'm going to do F equals ma. Cat's moving down, so I'll make that down positive. Mass times gravity minus tension equals m times a. Because this tension is causing that to rotate, we'll use the rotational equation of that. Torque is I alpha equals Rf. In which case I already know the I value. It's that 1/3 ml squared. My alpha value, I can make that be linear, A over L 1/2, because the radius is still 1/2 of the length. And over here for the force, I'll have my tension, and the distance from the tension will also be 1/2 L. Now I have two equations to unknowns, my tensions and my accelerations. I'm looking for tension here, so I want to solve one of them for acceleration and plug it back into the other one. So this one, if I solve for A, I'll have mg minus t over m. And this one, if I solve for A, let's see, I can get rid of all of my L's. Divide by L, divide by L. I'm going to multiply by a half, which will give me a fourth over here. I'm going to multiply by 3, and I'm going to divide by m, and that'll give me that the acceleration is 3/4 t over m. Then I can set those equal to each other. So my two m's will cancel out. Multiply this by 4, 4mg minus 4t equals 3t. Add that over and say 7t equals 4mg, and then I can say my tension is 4/7 mg. D. Determine the angular acceleration of the hoop and rod assembly. E. Determine the linear acceleration of the cat. I think it'd be easier to do this one first because we already have our linear acceleration value here, so we could take and plug this back in. Say A is 3/4 of 4/7 mg all over m. Our m's will cancel out, our 4's will cancel out, and that leaves us with a linear acceleration of 3/7 g. Then remember, our angular acceleration is always equal to the regular linear acceleration divided by the radius. So if I take my linear acceleration, 3/7 g, and I divide it by the radius, 1/2 L, that gives me a value of 6/7 g over L, and that's my angular acceleration. Lastly, part F, after descending a distance of h being 5/3 L, the cat lets go of the string, and at that point, what is the angular momentum of the cat? So remember that the angular momentum equation is I omega, which is the same as mass times velocity, inertia times rotational velocity. So that's our angular part of it, and then our linear part is going to be RMV. Now, is the cat moving in a straight line, or is it rotating? It's moving in a straight line, which means I'm not dealing with the angular part. I have to deal with this linear part. Again, the radius is 1/2 L, because that's how far away from the pivot point the line of motion of the cat is. Then for the mass of the cat is m. And lastly, we need to find how fast is the cat going once they get to that point. And much to your chagrin, I'm going to opt to do what you always do, and that is pick kinematics. So I have a final velocity. Since this is a height, I'm going to have to do the squared one, vf squared, vi squared, plus 2ax. The initial velocity of the cat is 0. The acceleration of the cat we set up here is 3/7 g, and the x distance that the cat goes is 5/3 L. Square root that, and that's our final velocity. Anything to simplify, we could get rid of our 3's. 2 times 5 is going to be 10, so I'm going to have 10/7 GL square rooted as our VF. Unfortunately, there's nothing easier to do with that, so I'm going to just place it up here, square root of 10/7 GL. And I'm going to just opt to leave it like that, because it doesn't look like there'd be anything you could simplify to cancel out. You could take this L and put it into there and square root it and get a fraction, but it's just as easy to do that. And that's how you do that particular problem.